Hi, my name is Shih-Han. I'm a postdoc at UT Austin. Today I'm going to talk about the joint work with Scott Aaronson on certified randomness expansion from quantum supremacy. So I'll start with a brief overview about random circuit sampling and linear cross-entropy benchmark. Then I'll talk about our certified randomness protocol based on this test. So the family of supremacy proposals that I would like to focus on today is sampling-based supremacy proposals. So the idea is the following: ask the verifier asks the device to sample from a distribution, which is supposed to be classically hard to sample from. So in the context of random circuit sampling, the verifier samples a random circuit which is made of 1 or 2 qubit random unitaries. The verifier samples C, a random circuit C, and the device is expected to run the circuit C on the 0 state followed by a standard basis measurement. So in 2019, Google uses this idea and uses the idea of random circuit sampling and claim that their 53 qubit processor Sycamore can pass a test called linear cross-entropy benchmark. The test itself is simple to describe. The device samples gets K samples and send them to the verifier. The device is set to pass a test if the average of the density on the samples is above some threshold, b divided by 2 to the n. So to get a sense why this test distinguishes a quantum from classical machines, it is known that for random unitaries, a perfect quantum computer can achieve a score B, which is approximately equal to 2. On the other hand, Google's experiment in 2019 can achieve a score 1.002. So the reason why it is very close to 1 is because of noise. On the other hand, as shown by Scott Aaronson and colleagues, it takes a classical exponential time to achieve a score which is bounded away from 1. On the other hand, it remains debatable whether Google's setup already rules out a classical simulation. In fact, there have been classical spoofing results for Google setup over the past few years using a method including construction of the tensor networks. So a closely related problem to protocols that demonstrate quantum computational advantage is certified randomness. So why we want the motivation on why we want a protocol that certifies randomness is clear. The main motivation is that modern cryptography rely on high quality random numbers is to generate keys to encrypt sensitive information. And it is known that the cryptographic constructions are broken with numbers which are poorly random. On the other hand, we can use unpredictability of quantum mechanics to generate random numbers. So suppose we have a perfectly reliable quantum computers. What we can do is that we can apply a Hadamard gate on the 0 state, followed by a standard basis measurement. This will give you a fair coin. In reality, we don't have a perfectly reliable quantum computer. So it becomes an important question how we prove to the classical verifier that a string is generally random. By a string being generally random, we mean it has high mean entropy, not just pseudo-random strings indistinguishable from fair coins against computation efficient adversaries. So to certify random numbers, we actually want a test which can be performed by a classical verifier, such that any device that passes the test implies that its outputs must have high mean entropy, must be a high mean entropy string. More specifically, the metric, the measure of randomness that we want to talk about for today's talk is a smooth conditional mean entropy on condensate information. So say rho is a bipolar state acting on two systems X and E, and rho is a classical on system X. So the smooth conditional mean entropy of X on E is the number of bits to guess E X for any adversary given access to a system E. And a smooth variant of it excludes an unlikely event that occurs with probability at most epsilon. So over the past decades, there has been many exciting proposals from Bell tests and other settings. An idea that we want to withdraw from the analysis from Bell tests is the following. Because Bell tests robustly self-test EPR pairs, we can show we conclude that for any device that passes the test, which is with a score epsilon close to optimal, then the underlying state shared by the devices must be root epsilon close to an EPR pair. And then by the nature of EPR pairs, measuring an EPR pair on whatever basis yields a random number. And every eavesdropper that shares entanglement with the quantum devices, the marginal state cannot be close to an EPR pair, which means that it cannot pass the test with good probability. And over the past years, there has been many other settings, for example, based on hardness assumptions or in the QROM, but I'm going to skip the details because in this talk. So in the context of random circuit sampling, why is there entropy in devices' response? So short answer to this question is that quantum computers only have limited powers. So more formally, we formalize the idea in the following two different approaches. The first, if a device that passes a test deterministically, then we show that this will imply it solves some problem, which is supposed to be hard. And the other is in a random oracle model, we can show that every device that passes a test in a deterministic way must make exponentially many queries. So which means that any efficient adversary, any efficient device cannot pass the test in a deterministic way. So 5 years ago, Scott Aaronson, in a talk in crypto, proposed the idea of using random circuit sampling to certify random numbers. So the idea is the following. Initially, the verifier uses a short random seed to generate a pseudo-random challenge circuit. And then in each round, it samples a random circuit C, give it to the quantum device, which gives back samples from C. In the following rounds, with high probability, it reuses the same circuit as in the previous round. And with some small probability, it gives an update. And you repeat the process over and over until the verifier gets in sufficiently many samples. And then the verifier chooses a small subset of samples and then computes a density and checks whether the device passes a linear cross entropy benchmark with some threshold 1 plus delta. If the samples passes the test, then the verifier decides to trust all of the samples and feed them into a quantum-proof randomness extractor, whose output is a string statistically close to random numbers. In a stronger security setting, we consider eavesdropper who may listen to the quantum device's output by sharing entanglement and arbitrarily program the quantum device. So we want a protocol that is secure in this setting. So before we dive into the detailed analysis, that does verify that what nice probability we actually want from the test. So in particular, we want the protocol to be useful for noisy devices. So we still want the extraction of linearly many bits per round from a device that is moderately noisy. Also, we want spot checking, meaning that we only need to choose a small subset of samples to compute the density. So it will require, which means that we can reduce the verification burden because the computing the density is very inefficient. And also we want forward secrecy, which means that the generated samples are weakly correlated from the given circuits. We want device independence and the security against quantum side information, meaning that we don't assume that the particular internal structure of a quantum device and the entanglement sharing between the quantum device and eavesdropper. Finally, we want the entropy accumulation, meaning that the generated samples from the quantum device are weakly correlated. So analysis takes the following 3 steps. The first is to give a single round analysis for every device that passes the test with high probability, with high score. Then the von Neumann entropy has a lower bound, which is linear in the number of qubits that the circuit acts on. So we take 2 different approaches, one as mentioned in the previous slides. And the second step is entropy accumulation, which reduces multi-round analysis on the conditional mean entropy lower bound to a single round analysis von Neumann entropy lower bound. And then in the third step, to get net entropy, we show that pseudo-random functions against a pseudo quantum statistical zero knowledge is sufficient for this purpose. So the hardness assumption we consider is a hardness for solving the following problem. So the algorithm is given access to exponentially many circuits and the exponentially many samples. And then the question is to determine either whether the samples are sample for in each coordinate, the sample Si is sample from Ci, or Si is sample uniformly random, meaning that it is independent from the circuit. So the key claim that we want to make here is that if there is a quantum device that passes a test deterministically, then there exists a QCM protocol for this problem. But the idea is the following, that have be any quantum device that solves the problem. Then in the yes case, each Si belongs to the set Ci with probability b times greater than the no case. So the distinction will allow us to apply Goldwasser-Sipser's approximate counting AM protocol to distinguish the distributions. This is in sharp contrast to the periodic classical setting, where each Ci were a classical circuit. So if Ci were a classical circuit, then there would be a AM protocol because you can approximately count the number of grid random coins. So from the hardness assumption, we get von Neumann entropy lower bounds for a single round analysis. If we draw a ray curve, which is as a function of lower bounds, we obtain versus the fraction of a circuit that the device passes a linear cross entropy benchmark, we get a fine function. So this observation will be useful for the multi-round analysis. Then we give evidence why this problem is hard for QCM protocols in the following steps. So we show that every QCM protocol solving this problem must make exponentially many queries. The idea is the following, that the distribution on F conditioned on a fixed S be a D1S and D0S. So for every pair of circuits, for a circuit drawn from an yes instance, yes case, we can obtain a no case by modifying the circuit on 2 to the n over 2 random points. So this means that we can apply a search lower bound to show that this problem is hard for BQP algorithms. But it turns out the same argument can be applied to show that it is hard for QCM protocols. And then to handle a quantum device, we apply a strong direct product theorem due to Shih-Han, together with Aaronsen's idea on oracle separation between NP and the BQP/Q poly. But the analysis is quite involved, so I'm going to skip the details in this talk. The hardness assumption, we don't know whether the hardness assumption implies security against integrating an adversary. So to handle quantum science information, we consider an idealized version of linear cross entropy benchmark called X-Hawk score. So this is an approach which is more closely related to the analysis for Bell tests. However, there's a caveat here we want to solve. So for linear random circuit sampling, there's no robust self-testing property that's associated with random circuit sampling. At least currently, we don't know that yet. So what makes the connection between a device that passes tests with high score and entropy lower bound is what I'm going to talk about in the following few slides. So to make a connection, we use a lemma by Kretschmer in 2021, which says that every T query algorithms given Oracle access to a random unitary C can be approximated by a simulator, which given access to T over epsilon square samples to diamond distance epsilon. So given this observation, if a device, for any device that passes achieves a X-Hawk score at least 1 plus delta, the simulator outputs a given sample with probability delta. So in the following picture, we consider a simulator with given access to M samples from the distribution P, and it is challenged to output a given sample. Although this test looks quite trivial, it allows us to give a rigorous von Neumann entropy lower bound. So the conditional von Neumann entropy lower bound we get is delta times the mean entropy of P subtracted by a second order term minus second order term against unbounded Eve, which shares side information. This holds for every simulator that passes a protocol with probability delta. Then with overwhelming probability over C, the mean entropy of P sub C is n minus log n. So which means that the von Neumann entropy is at least delta times n. So to get a rate curve, which is von Neumann entropy lower bound versus the score the device achieves, we get an affine function. So this observation will be useful in the following analysis. Then for entropy accumulation, we give an entropy accumulation theorem which reduces multi-round analysis, I mean entropy, to a one-round analysis from the von Neumann entropy. The idea is the following. I'll say the rate curve is what you get in a single round analysis. And then you set a threshold, which says that okay, above the threshold, we say the device passes the test. And then we draw a fine function sits below the rate curve. This will be the bound per round in the multi-round analysis. So more specifically, we show that for any device that passes a test with threshold 1 plus delta, we get an affine function B of delta. This means that in the multi-round analysis, then any device that solves a linear cross entropy benchmark with threshold 1 plus delta, the smooth conditional mean entropy per round is B of delta. So this analysis follows closely to the previous analysis by these authors with minor modifications that is useful for linear cross for the test we consider in this talk. Then in the third step, we reduce the input entropy by using a pseudo-random challenge circuit. So to see how this works, let us first introduce the quantum-proof randomness extractors. So randomness extractor is quantum-proof if for any classical quantum state, which is classical on X, the conditional mean entropy is at least K. It implies that the output of the random extractor is random. Is a uniform string. It's statistically close to a uniform string in the presence of a random in the presence of the quantum information. And then about 10 years ago, Dave Postman, Vidic, and Renner showed that Trevisen's extractor is quantum proof with interesting parameters. So to reduce the input entropy, we can replace a random circuit with a pseudo-random one. But we want the pseudo-random function to be secure against a quantum statistical difference in presence of quantum information. So for what class QS quantum statistical difference is a complete problem? The answer is QSDK, quantum statistical zero knowledge. So we define a notion. We say that two function distributions are indistinguishable against a QSDK if for every pair of query algorithms A and B, the statistical difference, average statistical difference between A and B when F is drawn from D1 is indistinguishable from when the function is replaced with a function drawn from D0. So we said that QSDK secure pseudo-random function is a distribution over functions indistinguishable from random function. So does there exist a PRF secure against the QSDK? Yes, in our paper we show that relative to a random oracle with high probability, with probability 1 over random oracles, H sub k is pseudo-random under uniform K. So in summary, we give LRXEB as a protocol for certified randomness. This is the very first full security analysis for certified randomness expansion against quantum information based on non-interactive single device and sampling-based supremacy proposals. So I will wrap up with a few open questions. First is, can we get efficiently verifiable supremacy proposals that can be run on this hardware? So currently we have various supremacy proposals, but none of them can achieve the 3 desirable properties, which includes NISC-ness, meaning that it can be run on NISC hardware, efficient verifiability, and clear speedup. And can we get certified randomness based on other sampling-based proposals, including boson sampling or IQP proposals? And can we get based on random circuit sampling, can we get a weaker hardness assumption than the one that we proposed in this talk? Meaning that the hardness of QCM hardness for the hardness of LLQSV for QCM protocols. And can we get natural circuit ensembles that allows a perfect quantum device to pass the linear cross entropy benchmark with overwhelming probability? And also, can we get a security against the entangled adversary in the plane model? Currently, in the analysis in our paper, we can prove it in a random oracle model. But for security, for against the quantized information, can we get a security in the plane model? So this ends my talk. Thanks.